Howdy, howdy. This is Mr. Potter. Welcome to day 2 of our discussion of derivative functions. Yesterday we talked about what a derivative function was. And today we're going to talk more about the graphical implications of a derivative function. So I'm going to start with the example that we did yesterday. Yesterday we were talking about the function where y was equal to x cubed, and we calculated that the derivative function was equal to 3 times x squared. And what I plan on doing today is talking about how does this relate graphically. Remember that this derivative function is my instantaneous rate of change. This is also the slope of the tangent line. And so what we're saying here is that if I look at these points, my slope is determined by this derivative function. So if I were to make a table of slopes, here's x and y prime. If I try this for a value of -2, -2 squared is 4, 4 times 3 is 12. And so that means that I'm expecting a slope of 12 when x equals -2. Notice that that is a fairly steep line over here that we're expecting. And if our x value is -1, we're going to be doing 3 times -1 squared, which is 3. A line that's not quite as steep, but still has a positive slope. And x is 0. That gives us 3 times 0 squared, or 0, which means we have a horizontal tangent here. And this is one of those peculiar situations where the tangent line actually passes through the graph. But that's because my curve is starting to flatten out. The steepness of this curve is decreasing. And we can see that in our table as our slope goes from 12 to 3 to 0. And as I pass through the origin, my graph begins to become more steep. If x equals 1, I've got 3 times 1 squared, which is 3. And notice that the tangent line here at 1, 1 should run pretty parallel to the tangent line here at -1, -1. Obviously, it's not because of the way I've drawn it to scale, but it would be parallel if this was drawn more accurately. And similarly, if I let x be 2, I'm going to have 3 times 2 squared, which is 12. And so I end up with a parallel line here. Very, very steep, almost vertical, parallel to my tangent line here when x equals -2. So if I'm given a function, it's really easy for me to take a look at how my graph is changing by looking at the behavior of this function as x goes through its different points. Now, we can also do this backwards. So we can talk about, let's say I know my derivative function is y prime equals 2x plus 6, and I want to know what the behavior of my original graph is. So keep in mind that, again, y primes, these are slopes of tangent lines. And so when I'm calculating in this table, I'm actually calculating slopes, not necessarily y values. So if x is negative 5, that's going to give me negative 10 plus 6, or negative 4. If x is negative 4, that's going to give me negative 2. If x is negative 3, that's going to give me 0. If x is negative 2, that's going to give me a slope of 2. X is negative 1 plugged into my function gives me a slope of 4. And if x is 0, I get 6. And so what I notice is that as I'm heading towards negative 3, my function should be decreasing. And as I go beyond negative 3 to positive x, my function is increasing. But I also notice that this graph is actually going from steeper to shallower to more flat, and then starts increasing as well. So I really have this kind of U shape. So once I say that my graph passes through the point, say, negative 3, negative 3, once I know that my graph passes through a point, this really is the lowest point of my graph, because before this I'm decreasing. After this I'm increasing. So I can talk about the behavior of my function. For an x value of negative 4, I'm expecting a slope of negative 2. Well, if I'm looking at a slope of negative 2, that means to get to this point, I had to have gone down to and to the right one. So I'm looking at something over here. Similarly, when x equals negative 5, my slope should have been a negative 4, so that means I'm going over 1 and down 1, 2, 3, 4. And so I've got this curve where my graph is getting progressively less and less steep, tapering off here to a horizontal tangent at x equals negative 3, and now I'm ready to start increasing again. And it's almost as if I have an axis of symmetry along this line, because my slopes are increasing by the exact same amount. And so I end up with a function that looks very similar to this. And if I didn't know better, I would say that this is a parabolic curve. Of course, at this point, I don't know what this function is. All I know is that the tangent lines go from having a slope of negative 4 to a slope of negative 2 to a slope of 0 to a slope of positive 2, positive 4, and positive 6. So I can get behavior from a graph by looking at its function, by calculating its derivative, and vice versa. So that's really the idea here of one of the major uses of derivatives, because these are slopes of tangent lines. And so these really help determine the path of the curve. So this is what I'm looking at when I look at a derivative, the graphical implications of what's going on. Now, just as we talked about continuity from an endpoint, we can also talk about what the derivative is behaving like at an endpoint. Because if I have a curve that has a definite starting point and a definite stopping point, although I can't talk about this being a limit as h approaches 0, I could definitely talk about the limit as h approaches 0 from one side, because it certainly looks as if I have a certain slope for my tangent line. And I also appear to have a certain slope at my tangent line over here, even if I can't find a true limit because I don't have a limit from both sides. So in this situation, I can talk about the limit as h approaches 0 from the positive side of f of x plus h minus f of x over h, because I can deal with positive h values. I just can't deal with negative h values because they're not a part of my domain. And so I can talk about this as being the talk about this as being the left-hand derivative. Because it's what's happening at the left endpoint of my graph. Similarly, if I'm doing the limit as h approaches 0, I do need to restrict h approaching 0 from the negative side of my difference quotient, f of x plus h minus f of x all over h. And so this ends up giving me a right-hand derivative. And what this allows me to do is this allows me to take a look at a function that has boundary points or that is piecewise. And so I want to take a look at an example of a piecewise function. So I'm going to define f of x to be this way. I'm going to define it as x for 0 less than x less than or equal to 1. And I'm going to define it as 1 over x for 1 less than x less than 2. So looking at this graph, starting at the origin, I expect to have a linear relationship going up to 1, 1. But at this point, I'm expecting to get an asymptotic graph up to 2, 1 half. And so my question is, I want to analyze the behavior of what's going on at this point, where these two pieces meet. So I need to take a look at the derivative of this top function on its restricted domain, and the derivative of this bottom function on its restricted domain. So if I want to take a look at part 1, where f of x is x, then I'm going to be looking for the limit as x approaches 0 from the left, because I'm only looking at values that are to the left of that graph. I'm not looking for h values as x is positive. So I'm looking for f of x plus h, which is just x plus h, minus x over h. And of course, the algebra here is pretty simple. My x's subtract out. I've got a common factor in top and bottom. So I've got the limit as h approaches 0 from the left of 1. And because it's constant, I'm left with 1. And at this, it seems kind of like a dumb moment, because the slope of this line is a constant 1. I know that because that's the coefficient of x. And the slope is determined by the derivative. But if I try and do the same thing with this 1 over x curve, as I approach x equals 1, I need to look at the right-hand derivative, or the limit as h approaches 0 from the right. So I'm going to be looking at 1 over x plus h minus 1 over x, all divided by h. And this is a little bit more complicated. I need to get a common denominator here. So what I'm getting is the limit as h approaches 0 from the positive side. This ends up being x over x times x plus h minus the expression x plus h over x times x plus h. And all of this is being divided by h, so I'm going to treat this as a 1 over h here. Now, simplifying the numerator, I end up with x minus h over this common denominator. And this is being multiplied by 1 over h as h approaches 0 from the right side. And I notice that I've got another 0 pair here. And I've got an h factor in the numerator and an h factor in the denominator. H goes into this negative h negative 1 times. So what I've got is the limit as h approaches 0 from the right of negative 1 over x times x plus h, which is negative 1 over x squared. And this is obvious from the graph as well. If my slope is negative, that means my graph is going downhill as x increases. And if I look at this, all of my tangent lines would have a negative slope. From the standpoint of a true derivative, I would have to look at it this way. I would have to say that my derivative is equal to 1 for 0 less than x less than 1. And for negative 1 over x squared for 1 less than x less than 2. But notice that I'm ignoring this case where x is equal to 1 because the limit does not exist at x equals 1 because the limit as h approaches 0 from the right of my difference quotient is not equal to the limit as h approaches 0 from the left. And so this violates the idea that the left-hand limit can exist, the right-hand limit can exist, but the limits have to be equal in order for the limit as a whole to exist. And so I really can't say anything about what happens at x equals 1 except that x equals 1, our derivative is undefined. And in fact, there is no one true tangent line that really would be tangent at this point. I can actually draw an infinite number of tangent lines because there's an infinite number of slopes that would only touch that curve at one point. And this idea of when a function has a derivative is something that will be extended on throughout this chapter. So again, the question was the question that arose was when does y prime exist? Remember that the derivative function is a limit. And this is something a lot of people forget. I'm coming up with a function. It's derived from an existing function, but it is the limit as h approaches 0 of my difference quotient. So this limit can't exist unless the left and right hand limits are the same. So the left derivative hand derivative has to be equal to the right hand derivative. And without those being equal to each other, y prime can't exist at that point. As a matter of fact, y prime can't exist at any of the points where the left derivative is not equal to the right derivative. And so this brings into mind something that we talked about before, because we've talked about the three-step process for when a limit exists. We've talked about a three-step process for when a function is continuous. And in fact, there is a relationship between this continuity aspect and the limit existing that allows us to figure out when a derivative exists. And this is something we'll be touching on later in chapter 3. So at this point, I really wanted to emphasize the graphical implications here. What's happening to the graph? Because a derivative is a slope. It's the slope of the tangent line. So once again, this is Mr. Potter. Thank you for watching. Have a great day.